Welcome to Land Eco Lightning Talks and Thinking Like a Landscape with Dr. Kevin McGarrigle. In this 8-part series on the natural range of variability concept and current departure, I discussed the origins of the concept, definitions and variations, applications, and important considerations in the implementation of the concept. In this talk, part 8 and the last of the series, I'll talk about current departure. Okay, let's get started. So current departure, first, what is it? Well, current departure is simply an estimate of the magnitude of deviation between the current value of the state variable and its NRV. Remember that the state variable can be anything pertaining to the pattern and process under consideration, and there are myriad possibilities as we talked about in the last talk. But regardless of the variable, current departure refers to how much the value of that state variable in the current landscape differs from its natural range of variability. And recall that the natural range of variability can be estimated using a variety of different approaches. So as a couple of examples, in the left figure showing the box and whisker plots, we have the percent of the landscape in each of several stages. In the NRV, regardless of how it's derived, is depicted by the box and whisker plots, and the current value of the landscape is given by the red dashed horizontal line. And where the red horizontal line, that is the current value of the landscape, is outside that range given by the box and whisker plot, we can state that there is departure in that attribute of the landscape. And as you can see in this example, that there is departure pretty much across the board. Some several stages are overrepresented and some are underrepresented. On the right, for a different variable that is more appropriately represented as a continuum, we have a continuous distribution in the percent of the landscape in an open forest condition, given by the kernel density plot in the top half, which is simply a continuous depiction of essentially the relative probability of the landscape having any particular value of percent open forest in this case. And the NRV distribution is given by the area under the curve. And alternatively, that can be depicted as a box and whisker plot as shown in the bottom half of the figure. And the current value of the landscape is given as a single value, depicted by the red arrow there. And comparing the red arrow to the NRV distribution, determining how far it is away from that distribution or how it's positioned relative to that distribution is how we assess departure when the variable is continuous, as in this case. And just a quick note here, for those that are familiar with the Land Fire program, to remind you that it was one of the earliest attempts to quantify and map current departure, in this case in fire regime. And they did so in using what they called fire regime condition class, which in the initial application involved just 3 classes. In subsequent applications, it's been refined into more classes, but the principle and the approach is the same. And this was basically one of the first attempts to kind of quantitatively assess departure using a modeling approach, and then assign departure values into this classification scheme so that they could map departure across the landscape. And this was done primarily for the purpose of prioritizing areas for restoration treatment and for allocation of funding. So one of the challenges that we face in current departure assessment is determining how to measure the deviation between the current and NRV. In other words, what standard do we use? How do we actually measure departure? So, for example, is departure depicted as a binary, as simply in or out, or as a continuum? If it's binary, what percentage of the distribution do we use to determine whether it's in or out? So, for example, if we were to use the center 50% of the distribution, as is depicted in the box in the plot on the right, we would obviously get a very different determination of whether the current landscape is in or out compared to if we use, let's say, the 99% range of variation, depicted essentially by the complete distribution in the figure in the top half. So determining what threshold to use to designate whether you're quote in or out is problematic and ultimately results in a somewhat arbitrary decision. And what's critical here is if that approach is used to make very explicit the threshold that is used, because they can come up with very different conclusions depending upon that threshold. If the standard is continuous, we have to determine, again, how we're going to measure the magnitude of departure when we're not simply representing it as in or out, but what percent or degree of departure do we have? And whether the choice is to use a binary measure or a continuous measure can oftentimes depend upon the nature of the variable under consideration. In some cases, some variables lend themselves more to one approach versus the other. When the current condition is represented by a single value, as in the example shown here, we essentially have a single value for the current landscape, and then we have a natural range of variability to compare it to. So if we look at the figure on the right, and we use the area under the curve, the shaded blue area, that represents the NRV distribution for this variable. Once again, the percent of the landscape in an open forest condition. And the current value is a single value. And so how do we compare that to that distribution to represent departure on a continuum? Well, one approach is to compute the proportional deviation from the median and some designated upper or conversely lower NRV limit. So in this example, if we specify the upper limit of the natural range of variability to be a value shown by the vertical dashed black line, then the difference between the median value and the upper limit value is given by B. And the current value differs from the median as shown by A. And if we simply take A divided by B, we get essentially a proportional deviation. So if the current value was equal to the upper limit, we'd get a value of 1. If it was less than 1, it means the current value is within that NRV limit. And if the value is greater than 1, it means it's outside that upper limit. And if it's a value of 2, it means it's twice the distance from the median as the upper limit. So the departure is represented as a continuum. If the current condition is instead represented as a distribution, so instead of having a single value for the current landscape, we actually have a range of values. So as an example, if we take the percent of the landscape in forest openings of different sizes, and we bin those openings, as shown here on the x-axis, into essentially patch sizes, patch forest openings or patch sizes of certain size ranges, ranging from a tenth of an acre here up to greater than 5 acres. We don't have a single value anymore for the current landscape. We simply have the percent of the landscape that's in each one of those bins or each one of those forest opening patch size bins. And so this creates a slightly different challenge for coming up with a continuous departure metric. The current distribution is actually given by a full distribution depicted by the red bars in this figure. And the NRV, or in this case, it was an HRV, is given by the distribution in the black bars because the landscape has a distribution of patch sizes for each time step or each snapshot of the landscape under historical reference conditions. And so from that information, we can generate a distribution. So we have two distributions to compare here instead of a single value against the distribution as in the previous example. One way to look at departure here is with the percent dissimilarity between these two distributions, or the percent non-overlap, given by a metric known as percent dissimilarity. And interestingly here, in contrast to the previous example, the percent dissimilarity reflects essentially bidirectional departure. In other words, it doesn't differentiate between cases where the current bar is greater than the HRV bar or lower than the HRV bar. It simply represents how different are these two distributions. And you could get a high degree of departure in cases where the current condition exceeded the HRV or NRV condition, or when it fell short of, or some mixture of those two. In other words, it doesn't differentiate between the direction of departure. And that brings up this important point. The choice of departure metric may depend upon whether the concern is for unidirectional or bidirectional departure. In some cases, it may be that the concern is primarily for negative departure, where the current landscape has a value that falls less than that natural range of variability. So an example might be where the current landscape has less area in openings than under the NRV. And the concern might be to create more openings in that forest for a variety of purposes. Conversely, there might be a situation where the concern is for positive departure, where we're concerned when the current landscape has values that exceed the NRV. So for example, if the current landscape has a percent cover or a basal area that is much higher than the NRV, well, one might be concerned and again, design management actions to move that current landscape condition back toward the NRV condition. So one needs to be aware of whether the concern is for positive departure, negative departure, or perhaps either. And that can very much influence the interpretation of the departure metric. Another concern with current departure assessments is understanding and being aware of how much of the quote apparent departure is due to true departure versus potentially other causes. So in the example here, we have a trajectory over time in the contagion metric, a measure of overall vegetation clumpiness. And we see at time 0, which represents the current landscape, the value is quite high. So let's say on the order of, let's say 52. And then under the historical disturbance regime, the value decreases rapidly and then achieves somewhat of a stable, what we call a dynamic equilibrium. So clearly here, the current condition deviates from that stable range of variability. And we would like to interpret that as an indication of departure. And in fact, it may be true departure. But we also have to be aware that some of that departure may actually be an artifact of the data and inconsistencies in the data or in problems with the model. So there may be inconsistency between the spatial input data and then the output data from the analysis, or there may be misspecification of the model parameters. And these two possible explanations or contributions to the apparent departure are very relevant in HRV type approaches that use simulation modeling. So just as an example here, one of the causes of apparent departure in HRV is a possible inconsistency between the model input GIS data resolution and the model outputs. So as shown in these two images on the left, the input data representing canopy cover classes from no canopy cover up to closed canopy, you can see that the landscape is relatively smooth and coarse-grained, if you will, in part because human interpretation was involved in the mapping and there was some smoothing done to smooth the input data. But on the right, we see the output of a raster-based simulation model that has not been altered. And so it reflects the underlying true grain or pixelation of the data. And you can see these are very different things. And so one always has to check for consistency between the input data and the output data and ensure that they're the same, or to take measures to account for those differences. So some partial solutions, if this is the case for apparent departure, is of course logically to ensure consistency between the spatial inputs and outputs. That's clearly what you'd like to be able to do. But there may be cases where you're constrained and you're not unable to do that. So one possibility is to coarsen the model output through smoothing algorithms to essentially match the graininess of the input data so that we're comparing apples to apples. Or alternatively, to limit the analysis of the pattern in the output to composition metrics. and sacrifice the configuration metrics that are likely to be sensitive to this issue, or potentially choose what are known as area-weighted metrics that essentially downweight the contribution of the small patches to the overall configuration in the mosaic, and thereby that fine-grained pixelation in the output has less of an impact. So the important point here is just to be aware that when we measure departure and we state departure, we hope that it's all real departure, but we always have to be aware of and check for these other possible causes and make sure that they're minimal, or if they are apparent, take measures to minimize them. Another really important consideration in a departure assessment is understanding that departure or the lack of it at one scale may not necessarily equate to departure at another scale. And this can be very important and have some important implications. So in this example here, we had a case where almost all of the local scale units, in this case they were geophysical units, were within their NRVs. In this case, they were NRVs based on an HRV, but it doesn't really matter. But in almost all cases, the local units were within the NRV. Therefore, we might conclude that there was no departure, and we didn't have to worry about anything from a management standpoint. Yet collectively, if we looked across all of the units at the broader or regional scale, there was clear departure evident as depicted in this figure. So the figure on the right shows what it looks like when we combine the values for the local units across the broader regional landscape. And we have two distributions here. The current distribution is given by the red line in the area under the red curve. That is the distribution of this particular metric, which happens to be the percent of the area in these large greater than 1 acre openings. So that represents the distribution across these local units at this kind of more regional scale. And in the blue or green, the distribution under that curve represents the HRV or the NRV distribution. And you can see it's much broader and extends to much greater sizes on the x-axis. And in fact, if we calculate the mean under the current condition was a 1.91. And the mean under the HRV or NRV condition was an 8.88. So even though most of the local units were within their NRV, it's very clear and very apparent that there's substantial departure here at the regional scale. And specifically here, we could say there's roughly an 8% deficit in the current landscape in the percent of these units that are in large greater than 1 acre openings. So the important point here is that one always has to be very aware of the scale dependencies of NRV and be careful about interpreting a departure at one scale doesn't always mean that there's the same degree of departure or lack of it at another scale. So the major take-home message for today is departure, just like NRV, is extremely complex and can be measured many different ways. What's important is to be very clear and transparent and explicit in how departure is being measured. Be aware of the arbitrariness of binary, that is, in or out departure assessments, because in my opinion, continuous departure is strongly preferred. Be aware of whether the departure assessment is uni or bidirectional and what the implications are of those differences. And remember that departure, like NRV, is scale, place, and time dependent. Well, this is Dr. Kevin McGarrigle signing off from this episode of Land Eco Lightning Talks. I hope this talk has been helpful. I hope you join me for my next lightning talk. In the meantime, keep on thinking like a landscape.